Hi, my name is Reyne from the University of Sydney, and I'll be talking through sample problem S. Now, the first thing I like to do is to go through these three tests at the beginning. The test for unsaturation, we can see is negative, orange color remains, so we're not going to expect to see any double or triple bonds. The test for an oxidation, though, is positive. So the kinds of things we're looking for here are going to be primary or secondary alcohols, or potentially an aldehyde. So we're keeping those in mind. So we've got primary or secondary alcohols or an aldehyde. Keeping in mind, the carboxylic acid test is negative, no bubbles. Therefore, we're not going to expect to see a carboxylic acid. Now, I do tend to skip the IR and the mass spec. Actually, I won't skip the IR for once. Because I'm looking for an alcohol or an aldehyde, there's a very quick check that I can do in the IR, which will help to narrow this down for me. Because an aldehyde, as we know, is the carbon double bond oxygen, and our alcohols are our OH. And in IR, we would expect to see a carbon double bond oxygen at about 1650, and it would be sharp and strong. And if we look at our IR spectrum, there is no peak that matches that description. When we think about OH, we expect to see a peak at about 3500 and very broad. So broad because OH can participate in hydrogen bonding. There are heaps of little variations that can occur in that and the way that hydrogen bonding happens, meaning that the bends and stretches that it can undergo to produce an IR spectrum will vary in minute ways. And we can see a broad peak at about 3500. So this tells me that there's going to be an alcohol present. But we'll go back to our normal plan. So now that we've confirmed that there is an alcohol and not an aldehyde, let's shift on down to the NMR data so that we can kind of see that in action here as well. Now our carbon NMR, and I will label these 1 through 5, we can see that we have peak 1, 2, 3, 4, and 5. And as to match up, I guess, with our IR and our test for an oxidation, or the oxidation test, peak 1 is about 70 ppm, which to me suggests a single bond carbon-oxygen bond. So carbon has been de-shielded. The typical amount of something like an alcohol would be about 70 ppm. Peak 2, just over 40 ppm, tells me that this is likely a carbon that's quite close to the alcohol. And then peaks 3, 4, and 5 are just increasing distance away. So the de-shielding effect that comes from that electron withdrawing group being the oxygen diminishes over distance. When we come down to our proton NMR, we can see here quite a few peaks. It seems to be fairly messy, and that's just because we have several environments that are quite close to one another in terms of their shift, and therefore they're kind of overlapping. So this is where the table really comes in handy. But I do want to mention one thing. I think that there's been an error in the data that's been translated from this peak data, because this singlet, so let's just kind of say this is A, B, and then we'll say this is kind of like C, D, E, all clumped up in that weird space. And then we have F down here as a triplet. And in fact, actually, I reckon E is specifically that one. There's a strong doublet there, which we'll come back to in a moment. But if we look at the shift that's been reported for A and B, it seems to be way off. So I think there's just been an error here in the data that's been imported from the software. So let's cross this out, and we'll just eyeball it based on what we can see on the spectra. So A is going to be at about, I'd say about 4.7 or 8. And then for peak B, let's just say that that's going to be about 4.05-ish. I don't know. I'm just saying a value there to make it make a bit more sense. Now that we've got that out of the way, we really want to be thinking about how can we work out the structure of this based on what we can see for these peaks. And there are some that are a bit easier than others. So for instance, peak A being a singlet and being fairly de-shielded, I would hazard a guess that this is probably our alcohol. It's the second time I misspelled it. I reckon that's our alcohol. Alcohols notoriously do not interact with other proton environments, so they're almost always going to be a singlet. So that's a pretty safe bet. Conversely, right down the other end, we can see here that peak F, which is very much shielded, a shift of only 0.92, has a peak area ratio of 3, so there are 3 protons present. And it also has, or is, a triplet, meaning that by the n+1 rule, it is next to 2 protons in another environment. And that would make sense if you think about a terminal CH3 next to a CH2 that's a part of that chain. Because the terminal CH3, that proton environment is only next to that with 2 protons in it, and therefore a triplet would be seen. When we then think about which carbon that might be then, or which proton environment that would be, it probably can't be the signal at 1.17, that doublet that we see, because that has a peak area ratio of 3, which doesn't make sense if we have CH3 and CH2. So this one, I reckon, is another terminal CH3, which we'll come back to. I think it's going to be at the other end. So we have the CH3 that's furthest away from our alcohol, which would be peak F. And then I think that there's actually a CH3 at the other end, which is at peak E, which I think is closer to the OH. When we come to the peak at 1.36, we can see that it's a sextet in that it's got 6 peaks, and there's a peak area ratio of 2. Now, if we have 6 peaks, our multiplicity is 6. By the n+1 rule, that means that it's next to 5 protons. And if we think about our CH3, our CH2, if there was another CH2, this environment, which is what we're suggesting the peak at 1.36 is, has 3 protons next to it, 2 protons next to it, and that would give it a peak of 6 then, or a multiplicity of 6. So it's kind of all coming together. Moving on to our next option, we then have a peak area ratio of 2. Okay, so there are 2 protons. Again, that's suggesting to me a CH2, but this time we only have a multiplicity of 4. So we're seeing a quartet. Now, if we're building up our chain as we go, so far we've covered the CH3, the CH2, the CH2, and then this particular environment only has a quartet. 2 of those protons are accounted for. So by the n+1 rule, there's 1 more proton missing, which must be next to it. And if there's only 1 proton there, that to me suggests that that is the carbon that has the OH coming off of it. So I know I'm kind of doing a lot of hand gesturing here and talking it through, but that's the kind of thought process that I'm going through to get there. So far I have CH3, CH2, CH2, CH, which I think has the OH off of it, and then the CH3 that I originally talked about at 1.17. This lines up with there being 5 peaks in the carbon NMR. And what we really need to do now is confirm, are there actually 5 carbons? So based off of what we've got here, we can then go to our mass spec and start to count this up. Because in the mass spec, we've got a molecular ion of 88. That's the mass that we're looking for. So let's say that we've got, as a trial by error, say we've got 5 carbons. So we'd expect to be 60 of that. We know that there's an alcohol, so there must be 1 oxygen, which brings us to, doesn't bring us to anything yet, but 1 alcohol that would account for 1 oxygen that would account for 16. And now we just need to add up our protons. So we've got 3, 6, 8, 10, 11, 12. So we've got 12 protons equals 12. And if we sum those together, we get 88, which is great. That tells us that our assumption of how many carbons and protons are present matches our mass spec. If we come back to our IR, we can do our standard check to make sure there are no other functional groups. We've kind of already done that by saying that there is no carbonyl, there is an OH. We could also point out that we've got our CH stretch at about 3000. And then we've also got our peak about here, CH bend. It's a bit messy, but that's the ones that we would expect to see for an alkyl chain as well. And as normal, we don't really deal with the fingerprint region. It's too messy for us to really interpret. So let's put that all together. So based off of what I talked through with all of my hand gestures, we have a CH3 to a carbon that has our alcohol, to a CH2, to a CH2, to a CH3. And that matches up with all of our data. And if we were then going to name this, we have a 5-carbon chain. So it's going to be a pent. And we have an alcohol, and we want that to be the lowest number. So I would call this pentan 2-ol. And that would be your structure. Now, if you want to test yourself, you might like to go through and add labels to each of those carbon and protons or proton environments to match up against your carbon and proton NMR. But it might get a little bit messy. So I'll leave it here, and then that may be a challenge for yourself if you want to try and confirm what we've talked through. I'll leave it there. Thank you.